So it turns out that one of the most interesting things you can do with a capacitor is to put it into a circuit with a resistor, because the capacitor cannot dissipate any energy. The capacitor can store energy, and later on it can release energy. It's sort of like an energy piggy bank. You put the energy in, it holds onto it, and then later on it gives the energy up. A resistor, on the other hand, cannot store any energy. It can only dissipate energy. If you give energy to a resistor, it is gone. It will be converted into heat, and you will never see that energy again. So those two devices are very different from each other, and when we put them in a circuit together, they kind of have some interesting interactions. A circuit that contains both a resistor and a capacitor circuit is known as an RC circuit. It has nothing to do with remote control, anything. It's RC as resistor capacitor. So RC circuits have been very carefully analyzed, very carefully studied, and their behavior is very well understood, and it's also very important for electrical and computer engineers. As an example of this, if you remember back, we used a 555 timer circuit to create the clock signal for the sequential digital labs that we did. And that 555 timer is based inside of it. It's based on an RC circuit. So let's look a little bit of calculus here. We're going to start with the equation we've already seen, Q equals VC. Previously we said VC equals Q, but it's the same thing. I'm going to differentiate both sides of this equation with respect to time. So on the left I get dQ dt, and on the right I get dVC dt. Now dQ dt, that's just the definition of current, because current is the time rate of change of charge. And over here I know that C is a constant, so I can pull the constant out in front of the derivative, and I end up with C dV dt. So I end up now with equation 6, which is sort of one of the fundamental equations for capacitors. I of the capacitor, the current going through the capacitor, is equal to C, the capacitance, multiplied by the time rate of change of the voltage. That is kind of the fundamental definition of a capacitor's operation. And you'll also notice that it's a differential equation. Now, I know that most of you haven't studied differential equations yet. That's no problem. We're going to solve it together, so you don't need to stress out about it. And if you find yourself ever needing to remember equation 6, remember that there's a current and there's a voltage. Obviously, there's capacitance. But on the right-hand side, if you listen to that right-hand side as you say it, it says C dV dt. It all rhymes. And it sort of sounds like an Italian grandma, C dV dt. So if you say to yourself, okay, I know that right-hand side is going to flow real well, C dV dt, it's not going to be C di dt. That doesn't flow. So, oh, it must have been C dV dt. And then the only other thing that could go on the left-hand side is the current I. So equation 6, one of the most important equations from today's lesson. So we also know that this is a relationship between the current and the voltage. The two most important characteristics that an electrical or computer engineer ever wants to study, current and voltage, both appear in that equation for a capacitor. We have a similar equation for a resistor that relates current and voltage, and it was known as Ohm's law. It was like the first thing we studied in this class. So we know that V of t is equal to I of t times R. V equals I times R. And the fact that these voltages and currents are now time dependent doesn't change the fact that Ohm's law is still going to be valid. So let's look at a circuit diagram here. And this circuit diagram is going to have a capacitor attached to a resistor. Now there's no external power supply. Presumably at some point this capacitor has been charged up by some sort of an external source, and now the capacitor holds some energy. The question is, how long is it going to take that energy to be dissipated by this resistor? So we've got the capacitor over here has some energy. It's going to slowly release it, and the resistor is going to dissipate that energy. It's going to spend that energy. So it's like the piggy bank is slowly being drained, or like a tank of water is slowly being drained as the resistor here is going to dissipate the energy. Let's do Kirchhoff's current law at the top node. So that means we have current I sub C is flowing out, and we also have current I sub R is flowing out. So I sub C plus I sub R is equal to 0. We can then substitute what we know for I sub C. We know for a capacitor, the current is C dV dt. So I'm going to go ahead and say C dVC dt. I'm going to move I sub R over to the other side, so it's going to become negative. And by Ohm's law, I know that I is equal to V divided by R. So C dVC dt is equal to negative V sub R over R. But if you look up here, the capacitor and the resistor are in parallel with one another. So they actually have the same voltage. I've labeled V sub C and V sub R separately, but they're really the same voltage. So I can actually write that equation with just V as just the single voltage. Now notice here in equation 10, there's only one unknown. The only unknown is V. C is known, that's a constant. R is known, that's a constant. V appears in the left in a derivative. It appears in the right as a plain old variable. I'm going to go ahead and divide both sides of the equation through by c, so I end up with this version of the differential equation. Now, if you have studied differential equations, you know how to solve this problem, but you probably haven't. So you kind of have to take my word for the fact that this is the solution to that equation. Equation 12 is the general form of a solution to the equation that's shown in equation 11. Maybe you don't have to take my word for it, because if you take this term here and you plug it in both places where v appears in equation 11, take the derivative on the left, you'll end up with exactly the same thing. Because it turns out, remember, if you take the derivative of the exponent, you're going to have the chain rule is going to pull down an extra 1 over negative 1 over RC, and that negative 1 over RC is going to balance this negative 1 over RC. You'll end up with equality in equation 11. This k is an unknown constant of integration. Anytime you integrate, if it's an indefinite integral, you're going to get a constant of integration. We don't really know what k is unless we say that the capacitor was initially charged to a known voltage v sub 0. So if v of 0, v at t equals 0, was equal to v sub 0, then now we can evaluate k. And then it becomes just this equation here. V0, the initial voltage that was on the capacitor. How much voltage was the capacitor charged to? And then e to the minus t over RC is showing that that will have an exponential decay. That it will start out decaying very quickly, but over time it's going to decay less and less quickly. It will asymptotically approach 0, but it'll actually never get all the way down to 0. This equation 13 is also right there on the most important hit list of equations for studying capacitors. This equation with the exponential decay, you will see this equation over and over and over again in many classes in your ECE curriculum. So let's look at a picture here. This picture is perhaps worth 1,000 words, but it shows the capacitor voltage decaying over time. You can see that initially it's decaying very quickly. But as time progresses, it flattens out and it decays less quickly and less quickly and less quickly. And it kind of looks like it hits 0 down here at the right-hand side. It never actually reaches all the way to 0. It will slowly decay, but the rate of decay will itself get slower and slower, so it will asymptotically approach 0. But after a certain amount of time, and that time we're going to call tau, after a certain amount of time, we're down to about 37%, 36.8% of the original voltage. After another tau, we're down to 13.5% of the original voltage. After a third tau, we're down to 5%. After a fourth tau, we're down to 1.8%. And after a fifth tau, we're down to 0.7%. This tau is known as the time constant. And the time constant for these circuits is just R times C. And so it really couldn't be much easier. You simply take the resistance, multiply it by the capacitance, and that tells you what the value of tau is. So let's imagine that you calculate for a particular circuit, tau is 1 second. Well, now you know that it's kind of going to quickly decay over the course of 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. I guess I would say that after maybe about 3 or 4 seconds, the capacitor is almost completely discharged. Or for a different circuit, you might find that tau was 1 millisecond. You'd say, wow, that's going to go much faster. In the blink of an eye, the capacitor will be discharged. Or maybe tau would be 100 seconds. And then you're talking, oh boy, I got to wait like 10 minutes to wait for this capacitor to discharge. So when you're dealing with a circuit, with an RC circuit, one of the first things you might want to do is calculate tau, because that will give you a feeling for how quickly the system is going to decay. Whether it's going to decay over microseconds, milliseconds, seconds, hundreds of seconds. Heck, you could have a capacitor that would discharge over the course of days. It would take a long, long time for it to decay if you had a large resistor and a large capacitor. Remember that after 1 tau, you're down to about 37% of the original voltage. After 2 tau, 13.5%. After 3 tau, 5%. After 4 tau, 1.8%. And after 5 tau, 0.7%. By the way, everything in that table came from equation 13. Because if I plug in that t equals RC, well, that's going to be after 1 tau. And v sub 0 e to the minus RC over RC is e to the minus 1. And that's where you get this 36.8%. And after 2 tau and 3 tau and 4 tau and 5 tau. Of course, it continues, 6 tau, 7 tau, 8 tau, but we just don't tend to show that. And then just to verify for you that the units of tau are in seconds, if you take R times C, R is in ohms, C is in farads. An ohm is a volt per amp, and a farad is a coulomb per volt, so the volts cancel. Now you have coulombs per amp, and an amp is just a coulomb per second. The coulombs cancel. You have 1 over seconds, which is seconds. So if you take the resistor in ohms and the capacitor in farads, you get the time constant in seconds. So that's a lot of ground to cover. It's time for you to look at an example problem on RC circuits now, where you can look at a particular circuit, figure out the time constant, figure out what the equation is going to be for the exponential decay, and then say at a certain time, find out how much voltage remains on the capacitor.